Look at your hand right now. Touch the table in front of you. Feel how solid it is. Feel how real this room feels around you, how deep it stretches, how three-dimensional every corner appears to be. You have never once doubted that you live inside a space with depth, with volume, with room to move in every direction. But some of the most respected physicists alive today think that depth is an illusion. They think the universe you are sitting in right now might be a projection, a shadow, a flat sheet of information billions of light years across, somehow rendering itself into the three-dimensional world you believe you are touching. It sounds like science fiction. It is not. It came from a problem so strange that it nearly broke physics itself. In the 1970s, a physicist named Jacob Bekenstein was thinking about black holes. Black holes are supposed to destroy everything that falls into them. No light, no matter, no information should ever escape. But Bekenstein noticed something impossible. If you drop a book into a black hole, the information in that book has to go somewhere, because physics does not allow information to simply vanish from the universe. So, where does it go? Bekenstein made a strange proposal. He suggested that all the information swallowed by a black hole gets stored, not throughout its three-dimensional volume, but smeared across its two-dimensional surface, its event horizon, the very edge of the point of no return. Stephen Hawking picked up this idea and pushed it further. He showed that black holes are not perfectly black at all. They leak a faint radiation, now called Hawking radiation, and that radiation slowly carries the black hole's mass away, which means black holes eventually evaporate, which means somehow all the information trapped inside them has to escape too, encoded in that radiation, written across a surface instead of a volume. Here is the strange part. If the maximum information a region of space can hold depends only on its surface area and not on its volume, then something is deeply wrong with how we picture reality. A globe of space with twice the volume should be able to store far more information than a globe with half the volume. But the math says otherwise. The math says information scales with the skin of a region, not its interior. Imagine a beach ball. Its outer rubber shell can only hold so much information. If information capacity depended on volume, filling the ball with more air should let it hold more. It does not. It only depends on the surface. Now, stretch that idea to the entire universe. The three-dimensional world you live in might be limited, encoded, and fundamentally described by a flat surface at its outer boundary, like a shadow cast from something flatter than the shadow itself. This became known as the holographic principle. A physicist named Gerard de Hooft first proposed it in the early 1990s. Leonard Susskind, one of the founders of string theory, developed it further and gave it the name that stuck. Their claim was radical. Everything you experience as three-dimensional space, every object, every distance, every motion, might be a projection generated by information stored on a distant two-dimensional boundary. The same way a hologram on a flat piece of plastic can trick your eyes into seeing a three-dimensional image. You are not standing inside a hologram like a beam of light hitting a screen. You are more like the image itself, the projection, the output of a calculation happening somewhere at the far edge of everything. Does that make you feel real? In 1997, a physicist named Juan Maldacena gave this idea its strongest mathematical proof yet. He showed that a theory of gravity operating in a curved, five-dimensional space is mathematically identical to a completely different theory, one without gravity, operating on the flat four-dimensional boundary of that space. Two totally different descriptions of physics, one with gravity and one without, turned out to be the exact same reality, just viewed from two different vantage points. This equivalence is called the ADS/CFT correspondence, and it remains one of the most cited results in modern theoretical physics. It does not prove our actual universe is a hologram. Our universe is not shaped quite like the model Maldacena used. But it proves, for the first time with rigorous mathematics, That a universe with gravity, depth, and 3 dimensions can be completely rebuilt from information sitting on a flatter surface with 1 dimension fewer. The trick is not fantasy. It works. Somewhere. Carl Sagan once said that the universe is a place that has, so far, always been stranger than we imagined it could be. He never got to see this idea fully mature, but it fits his warning perfectly. Reality keeps refusing to be as simple as it looks. So, where would the boundary of our universe even be, if this is true? Some physicists suggest the cosmic horizon itself, the outer edge of everything you could ever possibly observe, might be the surface doing the encoding. Not a wall, not an edge in space, a limit built into information itself, sitting roughly 46 billion light-years away in every direction, quietly rendering everything inside it, including you, including this sentence, including the chair beneath you right now. Think about what that would mean for a memory, for a decision you made yesterday, for the feeling of sunlight on your skin. If the holographic principle applies to the entire cosmos, none of those experiences are stored the way you think they are stored. They are not floating inside the empty space around you. They exist as information etched onto a distant boundary, and the 3-dimensional version you experience is simply the readout. You would still feel real. You would still remember your own name. Nothing about your daily life would change. That is the unsettling part. A holographic universe would be completely indistinguishable, moment to moment, from the one you already believe you live in. Does that unsettle you or comfort you? Some physicists have gone further still, testing whether this idea leaves fingerprints we could actually detect. In the mid-2000s, a team working with an instrument called GEO 600, originally built to detect gravitational waves, noticed unexplained noise in its measurements. For a brief moment, some speculated this could be evidence of a grainy, pixel-like structure to space itself, the kind you would expect if reality were fundamentally 2-dimensional information being rendered into 3 dimensions. The noise was later explained by ordinary technical sources. But the search continues. Physicists are still hunting for evidence that space, at its smallest possible scale, is not perfectly smooth, but built from discrete bits of information, the way a photograph is built from pixels you cannot see until you zoom in close enough. Nobody has found that proof yet. Maybe nobody ever will. But the fact that this idea survives decade after decade, tested by some of the sharpest minds in physics, tells you something. It tells you that the boundary between what is fundamental and what is merely appearance is far blurrier than your senses will ever admit. You feel like you are standing in the middle of a vast 3-dimensional universe, depth in every direction. Distance you could walk for a lifetime and never cross, and maybe you are. Maybe none of this holds up beyond elegant mathematics. But maybe, just maybe, the space around you is not the fundamental layer of reality at all. Maybe it is the shadow of something flatter, something further away, something quietly writing the story your senses insist on believing. So, touch the table again. Feel how solid it is. Feel how real this room feels around you. And ask yourself gently whether the depth you feel was ever really there, or whether you have simply always been standing exactly where the universe wanted you to look.